Happy Eclipse Day, everybody. I'm excited and I get to ramble about space today, which is always something that I enjoy. I hope that you enjoy my rambling as well. Note that there is no in-person lab this week, so at the very least, there's no one that needs to be in a physics room this afternoon when the eclipse is happening. If you want to watch the eclipse, again, make sure you have already grabbed a pair of these. If you already have a pair, great. If you haven't yet, grab them quick. There's not many left. The eclipse will be starting in this area around 1:30. It'll hit as full as it's going to get for us around 3:30. For where we currently are, we're sitting at about 75% totality. If you've got anyone that lives in this trajectory, they will get to see the full total eclipse. But we're at about 75%, and that'll happen at around 3:30, and then the sky should go back to normal by about 4:30, is what I've been told. And I'm excited, and you should not look at it without these, very specifically because, one, you shouldn't stare at the sun in general, but two, the real danger of an eclipse is, since there is less visible light than normal, you tend to think, oh hey, this is fine, this isn't hurting, without realizing that there is a bunch of space radiation pouring into your retinas, burning them out that you can't detect. So that's the real danger of the eclipse, of staring at the sun in general. It's the light you don't see that can hurt you. Does that make sense? UV, not infrared. It's the UV and the other higher frequencies of space radiation that get you. So don't stare at the sun in general, and don't stare at the eclipse without that. And today what we're going to be talking about is the eclipse and also gravity and orbit. And some other space eclipse facts in general, because I very enjoy this subject and I just wanted to take the day to just talk about it. There is no in-person lab. There is one take-home assignment that I have posted onto Brightspace that will utilize all of these concepts in a very brief assignment. It's not a long one, it's just practicing the stuff we talk about today. It's already posted to Brightspace. I'll send out an email with it this afternoon as well. So make sure to work on that. It is officially due by the end of the week. Really, I just need it before grades are due at the end of the semester. So just treat that instead of your normal in-person lab for this week. Today will be eclipse. Wednesday we'll talk about sound waves, and then on Friday we'll start heading into a test 2 review territory to make sure everyone's ready for that before next week. Any questions right now? All right, in that case, let's talk about space. Eclipses are fun. There are 2 main types that we have on planet Earth, and the name of that type depends on which of the objects in question is being blocked from view. Today's is a solar eclipse, which means that the sun is getting blocked. This happens when the moon passes perfectly in front of the sun, blocking the light from it and creating a giant shadow, which looks something like this. This is a simulation created using a program called Universe Sandbox, which is very fun and accurate. It is literally casting a giant shadow where the moon passes in front of the sun, blocking its light. This is again what a solar eclipse is and does. And this is why you can only see it from specific angles. Depending on where you are on the planet, the moon is just physically not in the way enough to block the sunlight. I want you to note, though, that even in the absolute path of totality, the darkest it would get would maybe just look like nighttime, and maybe not even that dark. The reason for that being that even if the sun is totally blocked out, one, the moon can't catch all of the light, one of the fun parts of eclipses is you can see the corona of the sun. Basically, it's giant flaming atmosphere. Because the sun is not just a round fireball, it also has an atmosphere like Earth, except the sun's is on fire. And so this ring of light you're seeing around the moon is that corona, something that you can't normally see when all the light of the sun is coming in, but when it's blocked like this, it's suddenly visible. So the moon doesn't get all of the light, so you still see this with the eclipse glasses. And you can even, these little red bits here, these are like solar flares and prominences, giant arcs of fire that race off of the sun and then come back down because of magnetism. So it's just a really cool event, and I love pictures like this. You don't block all the light, and that's why at worst it looks like night outside rather than like the void of space. But even night on this planet doesn't get that dark because the atmosphere tends to catch and redirect light. So even if you are in, this particular path, light still bounces from the atmosphere into that zone. And that's why even the night side of the planet is never like total darkness. There's still light on that side because literally it conducts through the atmosphere to get all the way to the other side. So, which is good because humans need to be able to see when the sun isn't up. But that's why you can even see in the dark outside, even if the moon isn't up. There is still light bouncing through the air to the night side of the planet, and therefore into the full of the eclipse as well.
How often does an eclipse happen?
They actually happen pretty frequently. Eclipses occur several times a year. The question is whether or not you can see them from wherever you are. Both types of eclipses, that being solar and lunar. A lunar eclipse is when the moon gets blocked by Earth's shadow. So, sun, moon, Earth. This is a solar eclipse. And this one is lunar. Sun, Earth, moon. In this version, the moon keeps light from getting to us, and in this version, the Earth keeps light from getting to the moon, and then you can't see the moon. And these happen pretty frequently, because all of these objects are constantly moving around all of the time. The moon orbits us, and we orbit the sun. So all you need is one thing to even slightly pass in front of the other, and you get some type of eclipse. They happen all the time. It's just a question of how much blockage happens, and can you see it from where you're standing? Does that answer the question? The statistics that I most recently looked up say that events like this, to varying degrees, happen maybe 4 times a year. Again, all over the surface of the planet. And that total solar eclipses, which is what we're getting today, can be viewed once every 5 to 7 years, wherever you are. Which kind of lines up with the past couple of events. We had another total eclipse about 7 years ago, and then a ring eclipse about 5 years before that. So I still think it's a big important event because, again, it's every maybe once or twice a decade you get to see this sort of thing. And it's even rarer for it to be a total eclipse from wherever you're standing. The 2017 one and this one are a total eclipse, which requires the moon to be close enough to us to block as much of the sun as possible. But if the moon is further away, it doesn't block as much light, and you get an annular/ring eclipse, where you don't see necessarily the ring of fire of the corona, you just see a ring of sun, which is still too bright to stare at. That is the type that I saw in Arizona, summer of 2012 or 13, I don't remember which. And again, this is the path of totality for this particular eclipse. Questions so far? All right. Now, in physics, we like math. So we're going to talk about the math for how orbit is calculated. This is the math, therefore, that NASA scientists are doing constantly to try to keep track of where the moon is, where it's going to be, and when future eclipses will take place. We've talked a bit about orbit already, because orbit is caused by centripetal force. In order for something to move in a circle around something else, like, for instance, the moon around the Earth, or even the Earth around the sun, all these objects normally want to move in straight lines, because that's what inertia and momentum tell objects to do. If mass is moving, it wants to keep moving in a straight line. You have to literally force things to move in a circle, and we call that required force centripetal force, the center-seeking force that is going to draw the moon towards the center of the Earth, kind of acting like a leash, keeping it from leaving in a straight line, and instead keeping it at a fixed distance, roughly fixed distance, around us. Again, that's the centripetal force that we've been discussing. Centripetal force is equal to the orbiting object's mass times centripetal acceleration. You need some amount of force to play this part. It's not always the same kind of force that does it. There's situations like this where tension in a string is what causes centripetal force. But in space, gravity is playing that part. Whatever's playing that part, though, you need enough centripetal force to cause enough centripetal acceleration in your mass. This would be the mass of the moon in this scenario, if we're looking at the moon's orbit. So moon's mass times centripetal acceleration. This basically tells you how quickly the moon is changing direction, and that AC is equal to either linear v squared over r or omega squared times r. Linear v is linear straight line velocity, the speed, the velocity that the moon wants to move at in a straight line away from us if it could. And omega is angular velocity, which is just its rate of rotation. The moon's rate of rotation is about once every 28 days. In both versions, though, the r is the distance between the center of the Earth and the center of the moon, because the center of the moon is very specifically orbiting the center of the Earth. That is where the gravitational effects of both objects are concentrated. So the r here is the distance between those 2 points, which is, we call it radius because it's the radius of the giant circle that the moon creates as it orbits us. So it's straight line distance from core to core, and we call it radius because it's part of the big circle. Now this all should be review. We covered this in the rotation chapters. Sound familiar? Okay. So, what NASA scientists do with these equations? We've got centripetal acceleration, centripetal force, and in space, gravity is what's playing the part of the centripetal force. So that means that you can set the force of gravity from the Earth on the moon here equal to centripetal force. If something is playing the role of centripetal force, you can just plug that number in for Fc. So you take the weight of the moon, the force of gravity pulling the moon towards Earth's core, and you put it into the centripetal force formula. Therefore, Fg on the moon, acting as an Fc, is equal to the moon's mass times the moon's velocity squared divided by its orbital radius. And you can use this to keep track of how quickly it's moving and where it should go next, and how far away it is, which is important to keep track of because the moon is drifting away. More on that later. Go right so far? Okay, now, over millennia, humans have done a pretty good job of estimating constants like the mass of the moon, the speed of the moon, and how far the moon is away from us at any given moment. So these are constants that you can Google, usually. We have tables with these numbers on them. What is less publicly available is how much does the moon weigh given where it is? Like, what is the value of the force of gravity between the Earth and the moon? Up till this point in this class, if we wanted to find the force of gravity acting on something, we would take its mass and multiply it by g, which we've been using -10 for that. Do you think this method will work for determining the weight of the moon over there? Why will it not work? It's because this 10, or more accurately, this 9.8, if you want to be very specific, this value is the strength of Earth's gravitational acceleration on Earth's surface. That value only works on Earth's surface, which we take advantage of in this class because most things humans examine are on Earth's surface. But the moon's not on Earth's surface, which is good for several reasons. But unfortunately, since it's not here and instead out there, this 10 isn't accurate at that position. So we need a different method. Now, I want to stress, there is gravity in space. Leaving the planet does not turn gravity off. There is gravity out there. It just gets weaker the further you are away from the planet. The astronauts are not weightless. They're just falling constantly in a circle, same as the moon. So there's gravity in space. I know this because Earth's gravity keeps the moon orbiting us. If that gravity wasn't there, the moon would leave, and then we don't have tides, and then we all die. Same with the gravity between the Earth and the sun. If that gravity wasn't there, we would leave the sun and freeze. So there's definitely gravity in space, which is good because we need it to stay alive. It's there, but it's not this. It's not this strength anymore in space. So we need a different, better, weirder looking formula to calculate space gravity. Or more accurately, a formula to calculate the gravity between any two objects, regardless of how far apart they are and whether or not there's an atmosphere between them. Because as it turns out, literally every object with mass creates a gravitational field. It is just an innate property of matter, solid, liquid, gas, plasma, or other, that matter just creates gravitational fields. Even single protons do it. All matter does it, and since all matter creates gravitational fields that then interact with the gravitational fields created by other matter, there's a force of gravity between literally any two objects with mass. The formula for this force is called the universal law of gravitation, which you can use to describe the force of gravity, again, between literally any two things with mass, which is exactly what we want to do here. The moon has mass, the Earth has mass, we want to know the force of gravity between them. And we call it the universal law because you can use it anywhere in the universe, whether or not you are on Earth's surface. So, this formula, force of gravity is equal to big G times mass 1 times mass 2 over r squared. To list each of these terms one at a time, big G is this. This is called the gravitational constant. Big G always means this number. You don't have to memorize it, it's on your formula sheet. It's just a very specific constant that we need to make this formula work. It has to do with the measurement of how gravity travels through open space. So this formula requires this number. Big G is not the same as little g. Little g is 10, big G is 6.67 times 10 to the negative 11th. Again, it's on your formula sheet next to the one formula that requires it. It's just a very specific constant with this one use. There's a lot of those in physics. So that big G is always that same number. It's just there next to the formula. You don't have to search for it. The other parts of this formula are big G times M1 times M2. You need to know the mass of your two objects to figure out the strength of the gravity between them. That's because the mass is what's creating the gravity. This does again mean any object creates a gravitational field that will exert gravitational force on any other object. That includes these two chunks of metal. They're both a kilogram each. And I've placed them here about 1 meter apart. Both of their masses are creating gravitational fields that interact with the other mass and the other gravitational field. So there's a force of gravity between the two based on how much mass they have, because it's the size of the mass that determines how big the gravitational field is, how much you are warping space-time by virtue of existing. More on that in upper level physics. So you need to know the two masses that you are trying to find the force of gravity between. The more mass you have, the more gravity you have. And then lastly, you are going to divide by a radius squared. This radius is using the term the same way it's used here, where it's really just the distance between the centers of the two items. The centers of mass being the center of the gravitational effect. And we call it radius because, again, it is basically the radius of a giant circle, the radius of the circular gravitational field. But it is just distance between both objects' centers of mass. In the case of the moon and the Earth, it would be the distance between the center of the moon and the center of the Earth. But if you're not dealing with planets, it's just the center of the item. These distances aren't big enough to make that much of a difference. But as long as you know those things, you can find the force of gravity between literally anything. Any two things. And it does have to be two things. One object creates a gravitational field, but that field doesn't act on anything unless there's something for it to act on. So, two things exert gravity on each other. One thing doesn't exert gravity on itself. Does that make sense? All right. Any questions, needs, concerns with the formula before we start practicing it? All right. First up, to kind of calibrate using this particular formula, I mentioned a second ago that I've got two 1 kilogram masses here positioned about 1 meter apart. Let's calculate the force of gravity between these two things. Our formula up on screen. Our two masses are 1 kilogram apiece, and they are situated 1 meter apart from one another. So, use the formula. We've got Fg equals a big G, 6.67 times 10 to the negative 11th. We've got times 1 kilogram, and then times a second 1 kilogram. It's one mass times the other. I just made them both 1 in this case. And underneath, we're dividing by radius squared. You want to make sure you are only squaring the radius, and I've just made the radius 1 this time for simplicity's sake. Bless you. Thank you. Also, bless anyone else who sneezed while I was talking. This is the type of physics math where we tend to plug in lots of big numbers. G itself, like this constant, is already kind of a big thing to type in. But this formula regularly uses things in very big numbers like the mass of planets and the distance between planets. So this formula will very commonly have very unwieldy numbers being typed into it. So you need to be very careful using this one in your calculator. Especially considering one of those numbers gets squared and everything else is divided by that number. You want to make sure that you are only squaring this thing and then dividing by that square. So I'm going to try to show how I would type these into calculators if you want to do this all at one line. I would type this in as 6.67 e negative 11, close parentheses, then 1, then divided by, open parentheses, 1 squared, close parentheses. That way the calculator knows to only square the one thing, take that thing, and then put it under everything else. Again, just trying to cut off some of the issues before they might happen. And now there's mostly just ones in this one, so this one shouldn't turn out that weird if you put something in wrong. The force of gravity that you would get between these two items, which since this is the actual mass and distance between the items, is currently the gravity on my table right now, is 6.67 times 10 to the negative 11th newtons. Do you think you'd ever notice a force that small? No, definitely not. The human nervous system is not that finely tuned. And I know you don't notice forces that small because you probably don't notice the gravity shifting as I move this thing around the room. I don't even know if that gravity is enough to make a hair on your arm twitch, frankly. So, gravitational forces are only really noticeable for very big objects, and that's why you notice the gravity of the Earth beneath you, but not of any of the objects around you. But you do technically still have a gravitational field. If we put these two weights in the void of space, so far away from every other object that this inward force of gravity is the only real force acting on the two of them, they would eventually drift closer together. And there's some lines of thought that say that's how planets got formed over time. Just pieces of rock slowly drifting together until they get so close to crumble up into a planet. I do want to make it clear, though, that this formula works both ways. Each object is exerting that force inward upon the other. This object is being pulled that way by that one, and then separately, this object is being pulled that way by that one. This force acts inward on both due to Newton's third law. It's not one on the other, it's both. Both is good. Make sense? Okay. Questions with the base number before I start changing it? All right. So just kind of see how things change if we manipulate a couple of different things. Let's say that I take one of those masses and I replace it with 2 kilograms instead of 1 kilogram. How is that going to change everything that follows it? Double. If you double one of the masses, you double the force of gravity. And you only have to double one of them, because just multiplying one of these by 2 multiplies the whole thing by 2. So the answer here would be like 13.3 times 10 to the negative 11th. Doubling one of the masses doubles the entire force of gravity inward from both. If you doubled both of them, you'd quadruple the force of gravity, really. Because then it would be 2 times 2 instead of 1 times 1 or 1 times 2. The opposite happens if you cut masses in half. If this was 1/2 times 1, you get half as much gravity. And if it was 1/2 times 1/2, you get 1/4 as much gravity. So gravity scales directly with each mass. Multiply one of them, you get double the gravity. Cut one of them in half, you get half the gravity. This is how you get kind of absurd situations like the mass of the Earth acting on us standing on Earth's surface. You know, Earth Earth's mass has 24 zeros after it. So it's creating a lot of gravity on our bodies. But technically, we exert the same force back. It's just that the Earth's mass is so big, that doesn't cause the Earth to accelerate. Not visibly, anyway. What about if instead of changing mass, we start changing radius? What happens to this number if you double the distance between the two objects?
Quarter of it.
Quartered, very good. If you change this one to a 2, 2 squared is 4, so now instead of dividing by 1, you're dividing by 4, and the final answer does get quartered to 1.67 times 10 to the negative 11th. Going further away from something weakens the gravitational pull, and that's why you are not consciously aware of Pluto's effect on your body. Frankly, you're probably not even aware of the moon's effect on your body. I'm certainly not. But this is why gravity does get weaker when you leave the planet. It doesn't go away completely, but it does get weaker. Related fact. This isn't quite a scale drawing, but in an attempt to make it kind of scale, let's say this X is the space station, which is, cosmically speaking, still pretty close to the planet. You know, they can see the Earth, they're orbiting around it. At this distance, the gravitational constant drops from 10 to 8. Weaker, but very much still there. And that's why if they weren't in the space station, they would eventually fall out of the sky. Frankly, the space station will eventually fall out of the sky. That's why it has to have rockets on it to make sure that doesn't happen. So, further away, gravity gets weaker. The inverse of that, if you say put in 1/2 of the distance, what happens to the force of gravity? Double. Well, quadruples, actually. Because 1/2 squared is 1/4. Dividing by 1/4 is the same as multiplying by 4. So the closer you get to something, the stronger the gravity gets. And that is why, if you ever try burrowing down to the center of the Earth, gravity increases until eventually you are crushed into a pulp and liquefied into magma. Which is why the center of the Earth is liquid and hot. It's under intense weight and pressure. It's also why we don't go there. Really, well, I think of it as a fun fact. You're allowed to think of it as you will. This constantly making the radius smaller and smaller and smaller, and therefore getting extreme amounts of gravity, is how black holes are formed. A black hole is basically, you take this formula and you make the radius super teeny tiny, like so many zeros, so many times 10 to the negative somethings. The smaller that radius gets, the exponentially stronger the gravity gets, until you just start warping reality and create a black hole. That's all a black hole is. It's just a planet shrunk down to the size of a volleyball with 10 million times as much gravity as it's supposed to have. Sound good? Questions? All right. One more practice calculation with this formula. We're going to start using some actual space numbers to show how ridiculous this can end up getting. Instead of two pieces of metal that are fairly close to each other, we're going to find the force of gravity between a person and the earth beneath their feet. Same formula, and G, big G, remains the same. But mass 1 is now going to be a 75 kilogram human, and mass 2 will be the Earth, which is currently estimated to be 5.98 times 10 to the 24th kilograms. this is why if you were at the center of the Earth, you would be reduced to the size of a pinhead. But we are not at the center of the Earth, thankfully. We are standing very far away from the center of the Earth. Specifically, we are standing 1 Earth radius away from the center of the Earth, because we are standing on what is roughly a sphere. This isn't quite the scale, but if our center of mass is here, that is 1 Earth radius away from the core. So the value we're going to plug in for R is the physical radius of the planet, which is 6,378,000 meters. I converted it to meters so that the unit works right. We're going to take those 6 million meters and square them, which is why it's very important to make sure you type this into your calculator correctly. You gotta square that big number and then divide by just that big number. Well, that is the formula itself for finding the weight of a human on planet Earth the hard way. Makes sense before I press enter on this metaphorical calculator? Alright. Again, I'll show how I would type this in if you wanted to do it all at once. I want to be very specific that you are only squaring the radius, and that that whole squared radius is what ends up underneath everything else. This is the scale of math that NASA scientists are dealing with all of the time, planet masses and space distances. And if my memory serves, this should spit out a value of approximately 735 newtons, which is the weight of 1 human being on planet Earth if their mass is 75 kilograms. Which, coincidentally, if you use the old-fashioned way, this formula, I'm using 9.8 so it's a little more accurate. Normally we use 10 in here, which is fine, but I'm using 9.8 so the number actually matches. 75 times negative 9.8 gives us negative 735. This value that we use here, the 10 or the 9.8, was determined using the big formula. This is just a very simplified version where someone has already plugged in the Earth mass and the Earth radius and found out everything for you except little m. So that was derived from this. Make sense? Questions? All right. Quick question. If this is the force that the Earth exerts on the human, how much force does the human exert on the Earth? Same number. Yeah, it's inward on both sides. Earth pulls human with this much force, therefore human pulls Earth back with this much force. If I weigh 1,000 newtons on planet Earth, Earth weighs 1,000 newtons on planet B. But the Earth doesn't accelerate because of that visibly, because that force on a mass with 24 zeros would cause an acceleration of about times 10 to the negative 24th, which you'd never notice. I'd never notice it. Besides the fact that there's also billions of humans over every square inch of the planet also pulling Earth in every other direction too. So even if it did amount to anything, it'd be canceled out by every other person and thing on the surface. So that's why Earth only moves because of space levels of gravity. But that's how the formula is used. Sound good? All right. Now let's talk about how you guys are going to use the formula in your take-home lab. I have in the take-home lab given a list of variables and a list of questions that will allow you to use all this information to calculate the moon's orbit, namely how far it is away from the Earth. In the lab itself, I kind of list out one formula at a time to solve for one thing at a time, but to kind of show the full orbit equation that NASA scientists use, basically, they take the centripetal force formula in conjunction with the gravity formula. The gravity from Earth on the moon is acting as a centripetal force, so they just set the two next to each other. Left side here, you've got the gravity formula. On the right side here, you've got the centripetal force formula. It's the same R on both sides because both concepts are asking about orbital radius. So it's the same R. You put the same number in those two places, or if I ask you to solve for R, it's the same R, you want to combine and simplify them. I've also tried to be more specific with the masses rather than just saying M1 and M2, because noticeably the mass of the orbiting object repeats from one side to the other. On the gravity side, you need to know the mass of both objects to find the force between them. So this would be Earth's mass, and this would be the moon's mass. The moon is a satellite. Satellite is just the specific term for orbiting object. And then on the centripetal force side, since the moon is the satellite and the moon is the thing undergoing centripetal motion, the moon's mass gets used over here. The mass of the moon would repeat between both sides, not the Earth's mass. Is that clear? Okay. That does technically mean that the mass would cancel out if you look at this from a multiplication sense, which means that any object, moon-sized or not, would have to move at the same speed at the same distance to orbit the Earth at that position. But if you do need to use the mass, then the moon's mass is what gets repeated. And so it's the same moon mass between both sides and the same R between both sides. Questions? Concerns? All right. Now, this is all very useful because it allows scientists to keep track of where the moon is, where it's going next, and also how far away from us it is, which is actually a pretty important detail to note. I mentioned that the gravity equation works in both directions. They both exert force inwards on each other, and so that means as the Earth pulls in on the moon, therefore the moon will also pull in on the Earth. The Earth doesn't move because of this, because the Earth's mass is too big, but the mass of the ocean isn't. And so tides happen when the moon's gravity literally hauls all the water over to one side of the planet. This is a very big simplification, but if the moon is here, this part of the planet's at high tide, and this part is at low tide. The sun also acts a bit in this, but major simplification, position of the moon affects the tides. Gravity of the moon affects the tides. And so we need to know where the moon is and how far away it is to figure out both where the tides are happening and how strong they're going to be. Which is especially important because the moon's not always the same distance away from us. It actually fluctuates. The moon's orbit is elliptical in nature. Frankly, most orbits are elliptical in nature, meaning that's the Earth, that's the moon. Its orbit is a little bit egg-shaped. So its distance from us is not fixed, and that means at any given point, its gravity on our tides is getting weaker or stronger. And that also affects whether you see a ring eclipse or a full eclipse, how far away it is. So we need to use this math to track its current distance from us, and we also need to make sure that its distance isn't getting further and further away over time, because the moon is slowly drifting away, and that would be bad if it leaves us, because with no moon we have no tides, and with no tides the ocean dies. If the ocean dies, we actually lose most of our oxygen, because most of our oxygen comes from sea plants, not land plants. So the moon is important, and we do all this math to make sure we know where it is and what it's doing. Sound cool? Any questions? All right. Again, make sure you've got these formulas accessible for your remote lab. Work on it over the week with friends or by asking me questions. You should ask me questions on your take-home lab, but I will not be in the building for office hours today because there's an eclipse to go watch. But email me and or find me any other day of the week. And have a wonderful eclipse day.